You've seen them, right? Those sprawling refineries and massive chemical plants, with pipes and towers stretching into the sky. While inside, immense forces are being controlled every single second. But what happens if that control is lost? That's what we're diving into today, the world of overpressure safety systems, the unsung engineering heroes that prevent absolute catastrophe.
It's a really good question when you stop and think about it. These places are just incredibly complex networks of vessels and pipes, all operating under extreme pressure, extreme temperatures. The amount of energy locked inside is just staggering. So, what is the last line of defense standing between a normal Tuesday and a total disaster? So in this explainer, we're going to break it all down. First, we'll tackle the main problem itself, overpressure. Then we'll look at how things can go wrong, and we'll meet the key piece of equipment that stops it. After that, we'll see where all that released energy is safely sent, and finally, we'll get into the incredible engineering foresight it takes to design these systems in the first place.
Okay, let's jump right in with the fundamental challenge here, this invisible but incredibly powerful force of overpressure. Just think about it for a second. Every single pressure vessel, every heat exchanger, every pipeline, it's basically a container holding back a tremendous amount of force. And that's totally normal. It's how these chemical processes work. The danger comes when the pressure inside suddenly starts to climb, way beyond what that equipment was ever built to handle. And here's the textbook definition. Overpressure is that moment when the internal pressure crosses a critical safety line. And when that happens, you risk a rupture. Now, a rupture in one of these systems isn't some tiny leak, okay? It can be a violent, explosive failure with just devastating consequences. So preventing this is, well, it's everything. So if you want to prevent failure, you have to understand exactly what causes it. So let's take a look at the anatomy of an overpressure event. You know, what's really fascinating here is just how many different things can go wrong. And these are all pulled straight from industry standards like API 521. A blocked outlet, that's easy to imagine. It's like putting your finger over a boiling kettle. But engineers also have to plan for things like a fire outside the equipment, a power outage that kills the cooling pumps, or even a tiny tube rupturing inside a massive heat exchanger. And this brings us to a really core principle in safety engineering. You don't design for double jeopardy. What's that mean? Well, it means you design for any one of those bad things to happen, but you don't design for two completely unrelated things to happen at the exact same time. Like a massive fire starting at the very same moment a control valve fails for a totally different reason. The odds are just considered astronomically low. But some scenarios are so fast, so violent that they kind of create their own rules. This quote points to one of the most dangerous events possible, a superheat limit explosion. Just try to picture this. A little bit of water gets into a vessel full of oil that's heated way, way above water's boiling point. That water doesn't just boil, it flashes into steam almost instantly, expanding with truly explosive force. A normal safety valve can't even react fast enough. And then you've got runaway chemical reactions. A tempered one is a little more manageable. The heat from the reaction makes the liquid boil, and that boiling actually uses up some of the energy, kind of putting the brakes on things. But a gassy reaction? That thing just produces more and more gas that can't be condensed, so both the temperature and the pressure just spiral completely out of control. These are two very, very different animals. Okay, so we've seen a bunch of pretty scary problems. Now, let's talk about the solution, the first and most important line of defense. The real hero of this story is the pressure relief device, or PRD. Honestly, the best way to think about it is like that little rattling valve on top of a pressure cooker. It is a purely mechanical device, no computers, no electricity, designed to do just one job: open up when the pressure gets too high and save the day. And how it works is just beautifully simple, which is why it's so reliable. Under normal pressure, it's sealed shut. But when that pressure builds up and pushes past a specific set point, that force literally shoves the valve open. It vents all the excess stuff out of the system until the pressure drops back down to a safe level, and then a spring slams it shut again. It's like a life-saving mechanical reflex. So the valve opens, it vents all this high-pressure material. But that begs the question, where does it all actually go? Right, because you can't just vent a cloud of flammable hydrocarbons or toxic chemicals right there in the middle of the plant. You'd just be trading one type of disaster for another. All that stuff that gets vented from the PRD has to be collected and sent to a dedicated, safe disposal system. And a lot of the time, that system is a flare. So you've got this big network of pipes called the flare header that collects all the vented gases. They flow into what's called a knockout drum. Think of it as a big tank that lets any liquids drop out. Then there's a liquid seal, which is basically a one-way door to stop any flames from traveling back down the pipes. And finally, all those gases go up the stack to the flare tip, where they're safely burned off.
So all of this, it leads us to the final and maybe the most impressive piece of the puzzle, the incredible engineering challenge of designing a system that can handle anything. See, engineers don't design these systems for some minor little hiccup. No, they have to figure out the single worst credible case for every piece of equipment. And a lot of times, that's a massive fire engulfing the vessel, which would cause everything inside to boil like crazy and create just enormous amounts of vapor that have to be vented safely.
So how on earth do they figure that out? Well, they use incredibly detailed thermodynamic analysis. Now, you don't have to understand what's on this chart. Just appreciate how complex it is. This is what engineers use to calculate exactly how much vapor a fire is going to create, literally turning pure physics into a number that saves lives. And this table here, this gives you just a tiny taste of all the other variables they have to think about for that one fire calculation. What shape is the vessel? How much of its surface is actually touching liquid? What's the most liquid it could possibly hold? Does it have any insulation? Every single one of these factors completely changes the final answer for how big that safety valve and the flare system need to be. So the goal, the entire point of all this painstaking analysis is actually really simple. Prevent the vessel from rupturing. It's all about making sure that the PRD is big enough to handle that worst-case vapor flow and that the flare system can get rid of it, keeping the pressure inside that vessel from ever reaching the breaking point. And that really gets to the main takeaway here. The safety that we see in these facilities, it isn't luck. It's not an accident. It is the result of decades of hard-won experience, all written down in engineering standards and brought to life by people who spend their entire careers thinking about how things can fail, all so they can build systems that are robust, reliable, and ready for the absolute worst. And that leaves us with one final thought to chew on. As we build bigger, more complex plants and we push our industrial processes to new limits, the challenge of anticipating failure only gets harder. How is the next generation of safety design going to evolve to protect an even more complicated world?